Welcome to day 18 of the Womanium Global Quantum and AI program. It is my pleasure to introduce our first speaker of today, Dr. Scott Crawford from NETL, the National Energy and Technology Laboratory in the US. Dr. Scott Crawford is a research physical scientist at NETL, the National Energy Technology Laboratory, where he develops optical sensing materials and platforms for energy-relevant analytes. He obtained his PhD in analytical chemistry from the University of Pittsburgh in 2019, and there he researched the optical and energy transfer properties of metal nanoparticles. Before that, he studied chemistry and economics at the University of Pittsburgh. Today, his talk will not only focus on the basics and concepts of quantum sensing, but then also heavily on the applications, some of which we see right now and not only in 10 or 15 years, as it is for many quantum computing applications. And we're really excited to hear more about that. Scott, please take it away.
Well, thank you so much for the wonderful introduction and invitation. It's a bit surreal for me to be here because, as you might have heard from the introduction, I'm not a quantum physicist by training. I'm an analytical chemist and material scientist. Nonetheless, it's just really excited to kind of give a very high-level overview of kind of the current state of the quantum sensors market. What are the technologies you can already go out and buy? What can they be used for? Then kind of looking at what are some other technologies that are kind of exciting that maybe aren't quite ready for commercialization yet, but have shown a lot of potential in lab scale demonstrations. And then finally, looking at some of the kind of exciting energy sector specific research trends for quantum, as well as some of the research priorities we've noticed from going through the patent literature. So hopefully you'll learn a lot and see kind of some of the cutting edge applications of where quantum sensing might impact the energy sector in particular. Because I am coming from a Department of Energy lab, I'd like to give you a moment to look over this disclaimer. And more importantly, I'd like to take this time to acknowledge the rest of the team. As you'll see, the quantum research program at NETL is fairly new. And I'd like to especially recognize Yuhua Duan, who's really helped build this from the ground up. He's the PI on the project and has really done a great job leading us into a few different directions, trying to build from the ground up a research program in quantum information science is not an easy task, especially because, as you'll see, there's so many diverse research directions from computing to sensing to networking. And he's really done a tremendous job leading those efforts. And so if you're wondering, how do you establish a quantum research program at an institution? Well, let me tell you how it happened at NETL. These efforts kind of began right after the signing of the 2018 National Quantum Initiative Act, which directed United States Department of Energy labs and other institutions to start incorporating quantum information science research into their energy portfolio. And so, NETL wanted to get an idea of, what's the current state of the field, and also what are the most exciting opportunity areas in the energy sector where we can actually apply quantum technologies. And so this culminated in a joint workshop held by the Pittsburgh Quantum Institute and NETL. The Pittsburgh Quantum Institute is a wonderful organization. It's a collaboration between the University of Pittsburgh, Carnegie Mellon, and Duquesne University. And this workshop, again, just kind of probed what's the current state of quantum technologies, how are they relevant for the energy sector. And out of that workshop, we started NETL Quest, or Quantum for Energy Systems and Technologies. And we have a few different goals. I think most challenging and most important one, of course, is to build an in-house quantum information science research program. But in addition to that, it also involves collaborating with other entities relevant to quantum information science. So organizations like Womanium and the Pittsburgh Quantum Institute. So we got a chance to work with some really wonderful people, attend quantum information science meetings and workshops, again, events like this. And I think one that is particularly important and particularly exciting is training the quantum information science workforce, both in-house and through internships, outreach events, et cetera. As you'll see, quantum technologies are already on the market. The field is projected to grow significantly across the board in the coming decades. And it's going to grow around the world, right? It's not located in just one region. On every continent, there are countries investing in quantum research, coming up with quantum strategies. And so there's going to be a huge demand, I think, for quantum savvy workforce. And so events like this, I think, are tremendously exciting and tremendously important for meeting that future demand. And I do want to note, we do have an external facing website if you'd like to learn more about some of our interests, some of the work we're involved with, or if you're interested in collaborating, please feel free to visit some of those sites. Okay, so you want to build a quantum research program. We had the workshop. The next step was to, we thought the best way to kind of get involved in the field and familiarize ourselves with the current state of the art was to actually begin writing a series of review papers. And so we decided to break this down by looking at kind of the 4 different pillars of quantum information science. So you have quantum sensing, which will be my main focus today, quantum networking and communications, and then also quantum computing and simulation. And so what this led to was the publication of 3 different review papers, and they're all open access. So certainly if you're interested in reading more, I encourage you to take a look at those papers. And they all sort of followed the same structure. So we begin, for example, looking at quantum sensors. We'd begin by kind of going over the basics. What is a quantum sensor? What are the principles of quantum sensing? What are some advantages quantum sensors might offer versus classical technologies? What are the qubit platforms that are used? And for each qubit platform, what quantum sensing technique can specifically be used with those materials? But after kind of going over those fundamentals, I think the unique aspect of these review papers is we then began to look at the energy sector and identify opportunity areas for these quantum technologies to be deployed. So when you think about quantum sensing, for example, you can envision the importance of infrastructure monitoring. You know, if you have miles and miles of pipelines carrying flammable gases like methane, you want to make sure those pipelines are structurally sound. You want to be able to rapidly identify and mitigate any gas leaks that might occur. So that might be one area where quantum sensors, techniques such as quantum LiDAR, for example, could be very useful. Grid timing, as you'll see, electrical grid synchronization. There's an opportunity there for atomic clocks to be used, for example. And so that was sort of the flavor of that review paper. We followed that up with one focused on quantum computing and simulations. And again, same type of story, looking at the kind of basics of quantum computing, looking at the different qubits that are used to build quantum computers, what are the currently available platforms, who are the major commercial players, and then from there, trying to look at what types of questions in the energy sector quantum computers could help answer. I think one that really stands out, for me as a chemist, of course, is reaction modeling. If you're looking at very large systems like metal organic frameworks or metal nanoparticles, those are very difficult and they're very computationally expensive to model using a classical computer. With a quantum computer, that might be much easier. Grid optimization, simulating fluid dynamics. These are all problems of significance to the energy sector. All of them require high performance computers, and quantum computing could certainly play a role in addressing those needs. And just to highlight, I think, the promise of these technologies and how accessible these technologies are, we've had a few different publications now in the field of quantum computing and simulation through an LDRD grant. And in this paper in particular, I want to highlight that the lead author was actually a summer student. And this paper focused on using a quantum simulator to look at the interaction between carbon dioxide and amines. So this is a really important process for carbon capture. It's a really hot topic of research right now. And so this was a really nice demonstration of how even today, we can find significant benefits applying quantum simulation and quantum computing to address problems of relevance to the energy sector. And then the third review paper that just came out last fall focused on quantum networking and communication. And in the energy sector right now, data is becoming increasingly important. So you have distributed energy resources from things like solar panels, wind turbines, fuel cells, and those often rely on microgrids. So you have these kind of smaller grids connected to larger structures. So you can kind of combine fossil fuel generated energy as well as energy from these distributed energy resources those are very vulnerable to cyber attacks. And that's always a major concern. If you have a cyber attack that could disrupt energy production, energy consumption, and have devastating consequences. So that's something we want to make sure that the data that we're collecting and transmitting it's secure, that it can't be hacked. Similarly, you hear a lot about smart grids and smart meters to optimize energy consumption. Once again, you have a lot of data being collected at those smart meters, and you want to keep that data secure. Electric vehicles and driverless vehicle networks, same story. And so the name of the game here is going to be using these quantum secure protocols like quantum key distribution to make sure that data is secure. And so this review paper was actually highlighted by front cover art, which is very exciting. So when you think about all these different technologies, I always look at quantum technology the same way that a viewer of Star Trek in the 1960s might have viewed the cell phone. You can conceptualize it, you're familiar with the technology, but we don't actually see it implemented in our everyday lives, right? It took about 40 years to go from the communicators in Star Trek to an actual commercial technology. When it comes to quantum, while it is true the field's in its infancy, in many ways the future is now, right? And by that I mean, if you look at any of these branches, quantum sensing, quantum computing, or quantum networking, you see the market value is currently already in the hundreds of millions, if not billion-dollar range. If you look at the projected growth over the coming decade annually, they're expecting massive growth, almost 30%, for example, in quantum networking technologies, almost 20% in quantum computing technologies. When you look at the commercial players, I think you have a really nice mix of large multinational corporations. So using quantum computing as an example, you have your well-established companies like Google and IBM, but then you have these startups that are also becoming major market players. And that's true, again, across the spectrum of quantum technologies. And then finally, you're seeing massive amounts of both private sector and public sector investments in quantum technologies as well. And so that's really accelerating growth. So in many ways, yes, we certainly expect the landscape to change in the coming decades, like any technology. But certainly we're very much in a world where quantum technologies are available and are being used. So my focus today is primarily on quantum sensing. You have kind of three basic criteria that has to be met that I think is a bit, at least for me, I'm a visual learner, so I think explaining it is a bit challenging. But basically, you have to be able to, you have a two-level system, and you need to be able to initialize your system, manipulate your system, and read out your system. So how does that work in practice? I'm going to use the nitrogen vacancy center in Diamond as an example. It's a very commonly used qubit. It can operate at room temperature. So for quantum sensing, it's one of the more mature technologies that's widely studied. And so you have two levels, right? You have your ground state and an excited state. You can move between these levels through optical excitation and relaxation, right? So in this case, optical excitation, shining a laser on your system, fulfills the initialization criteria. But then within each of these energy levels, you also have different spin levels. And so it turns out that you can interrogate your system with microwave excitation. And when that microwave excitation is in resonance with this gap between your 0 and plus and minus 1 spin states, you can actually change the population of states moving from 0 to plus or minus 1 in your ground state. Now, if you apply this resonant microwave field, and now you do optical excitation, you in turn have a higher population now in the excited state in this plus or minus 1 spin state. And the reason why that's important is that you have a lower chance of relaxation through a fluorescence-based mechanism when you're in this excited plus or minus 1 state. And so practically what that means is you have a decrease in fluorescence. Okay, so the way this works, if you're monitoring your fluorescence intensity as a function of microwave excitation, when you're outside of resonance, when you're not at this 2.87 gigahertz range, your fluorescence won't change, right? It's going to stay pretty constant. And then as you get to resonance and you start to change the population in this plus or minus 1 spin state, now you get a decrease in fluorescence. And so that's your measurement. So your readout is actually looking at the change in fluorescence as a function of this microwave frequency. How do you actually use this for sensing? Well, it turns out that this plus or minus 1 state is degenerate, right? They're energetically equivalent. When you apply an external magnetic field, the degeneracy is broken. You have Zeeman splitting, and the magnitude of that splitting is dependent on your magnetic field strength. So how this manifests itself in a quantum sensing experiment is now you have not one dip, but two dips, and the distance between those dips corresponds to magnetic field strength. And that's just a very simple demonstration of how we can develop a highly sensitive quantum magnetometer using nitrogen vacancy center qubits in diamond. From a material science standpoint, just a wealth of different materials that we can use for quantum sensing. I used, like I said, nitrogen vacancy center in diamond, but there are plenty of other color centers that are being explored, and it seems like every day a new color center is being discovered. Silicon carbide is another really exciting technology, just from a potential for scalability standpoint. And again, there's a number of color centers in silicon carbide that are being explored that can also operate at room temperature. Obviously, things like trapped ions, cold atoms, atomic vapors, all very well established qubit technologies. Photonic qubits, where you use, for example, squeezed states of light, or another platform that's commonly used, particularly if you think about D-wave quantum computers, for example. And then you have some other technologies that maybe aren't as established yet, but show a lot of, I think, potential for future innovation. Rare earth element doped crystals, for example. Spin qubits and metal organic frameworks is another, I think, just really exciting area, because you can make these very well-defined structures that are porous, that are already widely used in sensing. So I think you could do a lot with these metal organic framework qubits for sensing experiments. But from a commercial standpoint, you're already seeing a number of fairly well-established quantum technologies using these different qubit platforms. So for example, one that we're excited about in the energy sector are these quantum gravimeters and gradiometers. For example, they can use atomic vapor cells to measure acceleration as a function of depth. And so where this becomes important, for example, is for resource discovery, right? If you want to discover oil and gas deposits, gravimeters are widely used for that. What's exciting about quantum gravimeters is they're self-calibrating. So classical gravimeters, you have to go through a series of calibration steps before making each measurement. That's not the case with quantum gravimeters. In addition to oil and gas discovery, CO2 storage sites, underground storage sites, is becoming a huge area of interest in the field. And that's something else that quantum gravimeters could be used in. Reservoir monitoring, discovering abandoned infrastructure. And what I want to highlight here is that these technologies are sufficiently rugged to, at the very least, now have been deployed in real field tests. And so in this example, a quantum gravimeter was actually taken to a volcanic site in Italy and actually used, over the course of, I think, a few months to make measurements. So you now have a technology that's sufficiently robust that it can withstand being in the field and provide usable data. And so I think we're very close to seeing these technologies come on the market. As you can see, there are already a few major commercial players in this area. Something that maybe is even a little bit more mature are atomic clocks. Of course, atomic clocks have been around for a long time, but I think one of the main innovations here, making the technology more accessible, is the ability to fabricate chip-scale atomic clocks. I've heard that now the next step is even producing wafer-scale atomic clocks, which is very exciting. And as you might imagine, as the name implies, you get extraordinarily precise timekeeping using atomic clocks. So some of the big energy sector applications, a lot of them actually relate to position, navigation, and timing sensors, especially in areas where GPS is difficult, where you can't get GPS signal. So for example, one method is called ocean bottom seismography. And so you actually have your atomic clocks on the bottom of the ocean floor, and you can use signal for that to get very precise navigation. Like I said, GPS isn't possible under those harsh conditions. And so that can be used for subsea resource discovery, for example. Another area where they haven't been widely used yet, but I suspect they'll become a lot more important, is actually as a backup timekeeping source in the electric grid. So in the electrical grid, time synchronization is extraordinarily important. Typically, they rely on GPS, but what happens if GPS goes down? So in this study, and this is a fairly old study now, I believe this came out in 2016, they used a chip-scale atomic clock as a backup time source. They went to see how it would function over a 24-hour period. And you can see over the course of a day, you had around a 900 nanosecond drift in your timing. So, fairly negligible. And so that was an exciting demonstration of how atomic clocks could be used in the power grid, for example. One technology that's not purely a quantum sensor, but relies on quantum processes and single photon detection, is quantum LiDAR, light detecting and ranging. There's a number of exciting applications here. There are a number of commercial players. The one I really want to highlight that I think is of the greatest relevance to the energy sector is actually monitoring gas leaks. So I mentioned before, methane gas leaks can have catastrophic impacts. It's an explosive gas, it's flammable, it's economically valuable. So of course, even if you don't have safety concerns, you worry about economic loss. So this is an example of actually being able to visualize and image methane gas leaking out of a storage site using a commercially available quantum LiDAR device. And then another technology that maybe isn't as well known yet as some of the others I mentioned, but is already commercially available and not terribly expensive, maybe $150,000, are these quantum diamond microscopes. And so they use the nitrogen vacancy center in diamond, the same qubit platform I was talking about earlier. And it can be used, for example, to image magnetic fields. So that's been used to study circuitry, photovoltaics, and I think one really interesting application from a security standpoint is detecting Trojan hardware insertions. So for example, if you import a chip and you're worried there might be some malicious hardware that was installed in that chip, you could use a non-destructive technique like the quantum diamond microscope to diagnose that and potentially detect malicious hardware. I believe right now the biggest consumers of the QDM actually are in geology. There's a lot of interesting geological information you can get by looking at different magnetic deposits in rock samples, for example. So these are some of the technologies you can already buy that are already of significant relevance to the energy sector. Some technologies I'm excited about that I think are a little bit, they're at a point where they've been demonstrated in the lab, but I think they still face challenges in terms of miniaturization and packaging to be used in everyday life, are instruments that are very relevant to analytical chemistry, which is kind of my area of interest. So one piece of instrumentation that's widely used in material science is atomic force microscopy. And so basically the way these work, you're basically rastering a very fine cantilever over a surface, okay? And if any features on the surface will cause that cantilever to be displaced. And so you can get very high resolution imaging of surfaces like thin films, self-assembled monolayers, etc. That cantilever displacement, measuring that displacement is shot noise limited. But by using a squeeze light interferometer, by integrating this quantum technology into an atomic force microscope, we can actually get resolution below that shot noise and therefore get much higher resolution imaging as a result. So I think this is one area, where you have a widely used technology that if it can be miniaturized and packaged, you could significantly improve upon classical AFMs by using these squeeze light interferometers. In that same vein, the same group in Oak Ridge has also done a lot of work on quantum enhanced Raman spectroscopy, again using squeeze light. And here you have two different effects. One is you're not only enhancing signal from your sample, but through destructive interactions, you're also reducing background noise. And so that gives you much higher resolution. Once again, it goes below the shot noise limitation that you typically encounter using classical sensors. So this has been demonstrated in the lab, both for spectral measurements, but also for imaging applications. And so for, again, for material analysis, for biological samples, the ability to make those types of high resolution measurements is critically important. And then using the nitrogen vacancy center in diamond, we can also make nuclear magnetic resonance spectroscopy measurements. And once again, this is one of the most widely used techniques in chemistry. Any small molecule, any polymer, any protein is typically going to be characterized using NMR. It gives excellent high resolution structural information for the material that you're looking at. And so by using the nitrogen vacancy center in diamond and using a series of microwave and optical pulses, you have an all optical method that allows you to extract NMR information. And my understanding at the current state of the field, we're not getting resolution yet that surpasses what we're obtaining on classical NMR systems. But the biggest benefits, at least in the short term, are that number one, we can significantly decrease the sample volume needed. So you can use up, so you have a really valuable sample. They've actually demonstrated quantum NMR using zeptoliter volumes. I don't even know how you begin to measure that, which is really exciting. And it can also give you really good spatial resolution. So if you're trying to do any kind of NMR that requires a high degree of spatial resolution, you can get down to nanometer length scales using this nitrogen vacancy center in NMR. So those are some technologies that I think we can expect to see come on the market in the longer term, and they'll have tremendous benefits for not just chemistry, but also biology, physics, medicine, etc. So from looking at the patent literature, what are some emerging areas in the energy sector where we can envision some of these quantum technologies being used that maybe aren't necessarily commercially available yet? So one, of course, hot topic are electric vehicles. We're seeing more and more electric vehicles enter the market. One of the challenges there, of course, is battery lifetime. How far can you actually drive before you need to charge your battery? The current classical technologies are about 10% accurate. You're about a 10% error on that estimation. So not too bad, but we're still building that charging infrastructure, so it can still be a source of stress if you don't have precise knowledge over how far you can drive. And there have been several groups in Japan in particular that have explored using quantum diamonds to estimate battery capacity. So they can be installed directly on the battery casing. They can operate over a wide range of temperatures that are relevant for driving a vehicle. And what's really exciting is under these conditions, they've demonstrated an improvement in the accuracy from about a 10% error to 0.2% error. So, well over an order of magnitude improvement using this quantum technology. Of course, for quantum navigation, again, using atomic clocks, particularly as driverless vehicle networks become more common. Several car companies have actually tried to patent using atomic clocks for navigation in their vehicles. That's another area where we can see quantum impact transportation. Something that might seem a little bit out of left field, but I'm including because it's near and dear to my heart, is metal ion sensing. So it turns out that as we continue to adopt these renewable energy technologies, the one trade-off is that things like electric vehicles and wind turbines rely on a number of really important metals, nickel, cobalt, lithium, and rare earths in particular. So you might have read about that on the news. So one of the challenges there is, can we produce enough of these metals to meet demand? Well, it turns out that one of the exciting potential sources of these critical metals actually comes from coal and coal utilization byproducts. So think about it. We've been burning coal across the world for hundreds of years, and you're left with this ash that's left over. It's a major pollutant. What can we do with that ash? We have no incentive to mitigate that pollution. We have no incentive to treat it. But there's a growing body of research demonstrating that we can actually extract significant quantities of high-value metals from things like fly ash and acid mine drainage. So we're killing two birds with one stone. We're getting rid of a major source of pollution, and we're also meeting demand for some of these metals. But the challenge is, of course, locating high-value streams of metals in the field, sometimes remote areas, and being able to monitor the purification and separations processes during downstream metal production. The current state of the art for metals analysis is very bulky, very expensive. So it'd be great if we could make something that's portable, highly sensitive, highly selective, and low cost. And so one of the technologies we could use, again, is that nitrogen vacancy center in diamond, because it is very sensitive to external magnetic fields. If you bring a high-value magnetic ion, like manganese or rare earths, near that diamond surface, you can use techniques like spin relaxometry and optically detected magnetic resonance to actually detect trace quantities of those high-value metals. Other examples I've seen in the literature that are less mature, but I think still interesting. This is an example of a quantum metal organic framework. They actually have an organic spin qubit embedded within the MOF, and they were, as a proof of concept, able to use a quantum sensing technique with this material to detect lithium ions. Geological surveying is another important aspect. We call it borehole logging. We basically are looking at geological features as a function of depth. So harsh environment, right? You're going deep underground, you're facing high pressure, sometimes corrosive environments. Here, a quantum accelerometer using rubidium atoms was developed, and you can see the packaging is very small, very compact, which is important for commercialization. So it's sufficiently compact to actually be put into a borehole, and it was lowered down to a depth of 50 meters, and it made a measurement at every meter. And so I think this is a really nice demonstration of how a quantum technology can be tested in a real world environment and still give usable results. So just a few examples of how we might expect to see some of these emerging quantum technologies be deployed within the energy sector. And then some, just really quickly, some priorities I'd like to highlight as well, some things that I think kind of in the overarching research, we get so lost looking at kind of these big picture exciting projects, we lose sight of what's really needed to actually translate these technologies from the research lab into a commercial product. One really important consideration is packaging, right? How do we make something that's compact? How do we make something that's rugged, that can withstand harsh environmental conditions, that you can actually manufacture, mass produce, and sell? So miniaturization is important. And I'm going to highlight in particular the nitrogen vacancy center in Diamond, those quantum magnetometers. That's a technology that they've made a lot of progress on being able to miniaturize through, for example, developing fiber optic devices. So you have integrated optics where you have your laser, you have your diamonds, all kind of on this little head that you can attach to an optical fiber. And so that can be very useful, for example, if you want to do long range distributed magnetometry, or maybe you can spread hundreds of kilometers potentially of optical fiber, and then make measurements and determine not only where maybe you're seeing changes in your magnetic field, but you can also get spatial resolution. So you can say, okay, 30 kilometers from here is where we're seeing this disruption in the magnetic field. And so that can be used, for example, for pipeline monitoring. So that's one exciting trend. And then also directly integrating your quantum sensing material with different sensor components. And so in the example I just used, I mentioned they're making these fiber optic magnetometers. One of the things you can actually do is directly embed your nanodiamonds right into your optical fiber. And so that gives you much better signal, and it also helps you make a more compact and more robust system. Another research group did something similar, but here, because you're not only worried about optical excitation, you're also worried about microwave excitation. They actually directly deposited their nanodiamonds on the microwave antenna, and that was found to also not only reduce the size of the device, but also boost signal. And then finally, from a material science standpoint, another major challenge for mass producing qubits is finding ways to improve scalability, right? Because material cost is still very high. Diamonds are very expensive. Maybe silicon qubits or maybe silicon carbide qubits will eventually replace diamond, but still you have to have good control over your process. You have to be able to mass produce your material with a high degree of control. And so just to give you one example of that, a group in Korea demonstrated using a series of masks through lithographic techniques to get excellent control over where their nitrogen vacancy centers are. So you have excellent positional and spatial control over your nitrogen vacancy center in your diamond chip, which is a very important consideration for developing high quality components for quantum sensing experiments. In addition to qubit fabrication, qubit functionalization is also very important. So before, when I mentioned ion sensing, this can actually be exploited for a number of different methods. So for example, let's say you want to do pH detection. This is something that's been done. You want to use your nitrogen vacancy center in diamond to detect pH. A change in pH won't change your magnetic field. So how do you go about detecting pH then? Well, what you can do is have a structure like this, where you have your nanodiamond, you have some sort of organic molecule attached, and then you have a magnetically active molecule, such as ion, such as gadolinium, near the diamond surface. So when this happens, your diamond is always going to be feeling the effects of the magnetic field from that gadolinium ion. But if you have a molecule on there that's pH responsive, let's say at a certain pH, that molecule begins to degrade. It begins to detach from the diamond surface. Now that gadolinium ion is no longer near the diamond surface, and so the diamond isn't feeling that magnetic field anymore. And so you can get very highly sensitive pH sensors by carefully functionalizing the diamond surface. And this has been an active area of research as well. So I think I see I'm already over half an hour. So I think I'll stop there. The only thing, from functionalization standpoint, this is what I'm working on with NETL. And essentially, the only story is here, we're just putting nitrogen vacancy center diamonds in a metal organic framework. Metal organic frameworks are porous. So it creates a unique scaffold where maybe we can have some control over what analytes reach the diamond surface and what analytes are excluded from the diamond surface. we're hoping this can be a strategy for, you know, improving quantum sensor performance by carefully functionalizing the diamond surface with a well-defined material. So with that, I will stop. Be happy to take any questions you have. Hopefully from this, you just kind of have a high-level understanding of what quantum sensing technologies are on the market, how the market is evolving, and some relevant use case scenarios where we can envision these quantum sensors being used within the energy sector and beyond. So thank you so much.
Fantastic. Thank you very much, Scott. And there are already questions coming up on the Discord channel. Scott, thank you very much for this very exciting talk that gave rise to many questions and ideas. We look forward to staying in touch and having you excite and inspire our audience in future programs and sessions. Thank you very much.
Thank you. Again, so grateful for the invitation. And it's just great to, now I can finally actually see who all is on the call. And I'm kind of overwhelmed by how many people. That's just, thank you so much for your time and attention. And please feel free to reach out. I'm sure, I think my contact information is on the slide. And if not, the organizers can get that to you. But you know, if there are any questions I didn't answer, always happy to talk more offline. So thank you again so much.